Alright, time for another draftphysics.com, debatephysics.com also. But alas, no willing human, uh, funky hair, to debate. Yeah, just nobody capable of exchanging arguments in the form of videos, which would be the way to do it. Whiteboards, explanations, all that kind of stuff. But nope, nobody can do that. So I don't think I need the arrow, so we'll get rid of that. All right, so I'll talk a little bit about springs, and and then maybe one little comment. It's not really worth even acknowledging. It's so redundant and useless. But anyway, it is what it is. That's what the internet produces. So let's get this mouse out of the way. Ooh, not very graceful, but it'll have to do also. Alright, so we'll try a different pen too. So spring. So something I have observed and I keep forgetting to mention. Another liability in these experiments, besides the carts having a bunch of angular rotation hiding their actual momentum in the wheelbase, springs themselves are really poor performers. Okay, so you can lose like 20% of the energy is lost in a spring. It's not a very good average. And so that's a huge liability in itself. But the other thing with springs is you can sort of understand that if I was to compress a spring and then release it, that the spring has a maximum velocity, okay, a maximum capacity to extend. So obviously if I put something on the spring to acquire momentum and it's very light, the spring can't push it, but it's maximum velocity, so it can't really, if I go a little lighter, I'm not going to be able to put much energy into it because the spring has a limitation. And the same is going to be true, so the lighter the object I place in front of the spring, okay, the less energy I'm going to be able to recover. This number goes up. So the lighter the object, the higher the amount of energy I'm not going to get, because the spring's going to be extending. It'll get to a certain velocity, which is the maximum velocity that the object can be pushed at, let's say. And then the spring is going to stop pushing at that velocity because this thing starts leaving at a velocity higher than the velocity of the spring. The spring's going to start moving slower, okay, as it's going out, and there's a point where the object it's pushing is going faster than the spring can go, and therefore the spring is going to extend, and then it's going to, do that wobbling thing, all right, with the remaining energy that it couldn't put into the object. And obviously, the heavier the object I put in front of the spring, the bigger the thing I'm pushing, the slower the spring has to move, and the slower it's going to move when it finally extends and this object leaves the spring. When the big object leaves the spring's only going to have a very little energy left. So it's going to give a lot more energy to big things than to very small things. So that should be understood by people doing science with springs as part of their experiment. They should understand that's a limitation of a spring, is that it's going to cheat the little thing and give a higher percentage of its energy to the heavier thing, just because of this fact that the faster things leave when the spring still has more energy to give. Just a fact. All right. So that was simple. So we'll move on to the next thing. So people just keep doing this. Well, what do you think happens when something crashes into something not moving? So here we have something not moving, and we're going to crash into it. And what is the expectation? And clearly my expectation is that whatever momentum this has is what you're going to end up as a total momentum, things moving. You have one thing moving, you have one thing not moving. After the collision, you're going to have some combination that still equals 10. You can't have negative momentum. All right, so essentially we're back to the 5 times the force, 25 times the energy argument, and I just sum that up with the scale argument again. So this is the theory they're defending. And I'm just saying, let's see, maybe I can do that in a clearer piece of space. All right, so I have a number of one weight objects, and I place them on the scale, right? So the first one goes on, and I get, by Hooke's law, 1 unit of weight. And then I put the next one on, okay, and now I have 2 units. So it's 1 and then 2, and I put the third one on, I have 3. Now your argument is that 3 times the weight is 9 times the energy, okay, and that twice the compression is 4 times the energy. So you do see how it gets kind of ludicrous, right? Because now I'm increasing by 5 here, okay, so putting this third one on, I increase the amount of energy by 5 units. And then I'm going to put one more on, and now I'm going to increase it again by another 7 units. And then it's going to be 9 units, when you finally get to 5. And it just gets higher and higher and higher and higher. And that makes no sense. I mean, to make the argument that when I put this 5th thing on, right, I went from 16 to 25 in terms of my kinetic energy potential. When of course I didn't. I just added one thing. It's the same amount as this one. It weighs 1. It can't weigh 25. And so the scale doesn't show what you're claiming to be true. So, physicist Michael says that kinetic energy is stored in springs. Well, the argument is where's the evidence of it? Because if you're really going to say that twice the compression is 4 times the energy and 3 times the compression is 9 times the energy, you can't just see how ludicrous that gets in terms of how easy it would be to create a tremendous amount of energy by just increasing the amount of weight you put on a spring. And obviously, if you had to convert it into a spring being compressed without gravity, okay, do you really think that if I go 5 times as fast, I'm going to compress the spring 25 times? No. So it's only going to be 5 times. So you're right back to this nonsense. I mean, you're going to concede that, oh yeah, it only compresses it 5 times. So where's the evidence of the 25 times the energy? Because I think that if I lock the spring at that 5 times the compression, I'm never going to be able to create anything with 25 times the energy unless I put something extremely light on the scale and pretend, because I got that increased velocity, that I conserved the energy. And you didn't conserve it because it doesn't exist. It's a simple argument. All right. So I need to say that better, I guess. I mean, you would think just saying the words, you really believe 5 times as fast as 25 times the energy. So I have to put in 25 times the fuel to go 5 times as fast. I mean, it's overtly what the theory says. You can't get around that's the obligation of the theory. And, so why can't you just answer the question and say, yes, that's what you actually believe, and that you actually saw some evidence somewhere on this planet indicating that's true. So just show me, link me to the evidence, because I can't find it, because it doesn't exist. So again, negative momentum. So we'll just go over it one more time. So, and I've said, look, it's fine. If you're going to make this contention that this is how it works, it's okay. Just show me an experiment where they actually capitalize on this. So again, their argument is I could have a 1 mass, and then I triple that for a 3. Okay. So I have a 1 and then a 3. And yeah, that's the best way to do it. And then I have a 9. No, tripling it would be a 16, wouldn't it? Yeah. No, tripling would be 9, yeah. Sorry. All right, and then I triple the 9. That's when it really starts getting big, right? So then I have a 27. All right, and so I could start with ounces, and then this doesn't get as onerous. But the idea would be then all I'm doing is I'm going to take a 1 mass. Well, I should start with a 3 then. Well, okay, I'll use this one. So I bang the 1 into the 3, and the 1 just starts with 100 momentum. And when it hits the 3 will have 130. And then when it hits the 9, we're up to Oh, I didn't do my math ahead of time. Oh, red doesn't show up all that well, does it? No, it doesn't. Yeah, you should draw bigger. If you're going to write smaller, you should draw bigger. That would be a good thing to do. All right, so I have to do 33% of 133. Well, anyway, so it adds like 70. Okay, so we could say 200. All right, and then I'll end up with 290 or something. So I just can keep increasing the momentum by banging lighter things into heavier things. And that simple argument. And you really think that physically does happen? That's a physical fact that it actually does happen in this world. And right now, nobody, no free energy nut, nobody has made the machine and taken advantage of the simple fact that you can increase the momentum. And you do know that momentum does do work, right? I mean, there's no denying, there's no experiment where you can take momentum and bang it into something and it doesn't do work on the thing you bang it into. So there's no doubt about the fact that momentum does work. So I'm increasing the amount of work you can do for free, okay, by just banging light things into heavier things. So anyway, this goes back to the experiment that physicist Michael was going to do and didn't do. Okay, so where you just make a pendulum and you end up with a scenario where you put 100 in. All right, you get 150 out. Oh yeah, I was supposed to use 150 in the example. That's why I was using the 3. So that was my bad. So it would be 150, and then this would be 275, 250. Yeah, almost. And then this would be well over 300. So it's even more of an increase with the heavier weights. Anyway, so I get 150 this way, and I get 50 back this way. And then you're supposed to believe, okay, that 150 crashes into 50, and you only get 100 out, and 100 goes back out. So 150 crashes into 50. All right, and somehow I only get 100, what I started with, back again. Can you understand how that really can't be possible, that you have this crash between the 50 and the 150? The only way you can get rid of 100's worth of the energy, because you have too much, is to create heat or something. And if you created heat, then that's energy you can't recover. So then how can you get all of what you started with back again and just do the experiment over and over? It recycles. It keeps going. It keeps doing this over and over again. How can it do that if it keeps destroying 100 of the momentum, converting it into heat? How can that keep happening? It can't keep happening. So obviously it doesn't happen that way. All right, this one hits, this one goes off with 75, okay, and this one goes back with 25, and then 25 hits 75, and you get 100 out. That's the obvious answer. That's the obvious what's really physically happening. And the fact that we don't have this experiment already done in 350 years, it's never occurred to science to even do the simple experiment of just dropping 4 pounds 1 foot and 1 pound 4 feet and measure how much impact energy those things have. They haven't even done that experiment. So the fact that you're convinced that this is good theory, and again it's a velocity squared, which why does that make sense to you? I mean, where in the universe could a vector, okay, with just a number attached to it, okay, how could that possibly be a squarable? How could it relate to anything in the universe in terms of squaring it somehow? Somehow the area of the velocity would be meaningful. I mean, how can the area of the velocity be meaningful? I mean, the only way you can make it meaningful is to understand that every vector has 2 components. But that's certainly not going to square anything. So, it's not going to square the magnitude. Obviously, the magnitude is only going to be some line that bisects that square. So you're just going to end up with, what you started with. Yeah, I don't know. It seems quite... yeah, I don't know. I don't know how to make this any simpler in terms of demonstrating how it doesn't make any sense. And you want to keep arguing it somehow makes sense to you, and you don't want to demonstrate it with what I'd argue are more valid experiments. Like I said, I've already pointed out flaws in the experiments that are available, and clearly the low friction carts with the tiny metal wheels is a really bad idea. I mean, you should be able to concede that's a really bad idea to make a cart that you're going to measure its linear velocity and presume its linear velocity to be all of its energy. Well, it's not going to be all of its energy if it's got metal wheels. All right. Yeah, so I can only reiterate what I've already iterated. So, all right. Let's see. I'll take a pause. I thought there was some other point I wanted to make, but maybe this is it. Oh, I just thought of it. Yeah, I just wanted to relate it also to the magnets have the same kind of flaw. And I didn't think about it, but it just occurred to me that when you think about using repulsive magnetism, so if I have two north-facing magnets, that it's going to have the same problem. So if I smash the two magnets together, right, I smash them right next to each other, and then I say, okay, let's see what they can push with that force. The trick is, if I put heavy things, right, very heavy things for the magnets to push, or one of them's nailed to the wall, it doesn't really matter. The fact is that the magnetism is going to be playing its game. It's an inverse square force. So understand the force is strong, and then it gets weaker and weaker and weaker by the inverse square law. So it's what's the word for that? You just have to appreciate that the force diminishes, okay, and it's time dependent and distance dependent from the magnet. Will tell you how much force you're getting. So the fact is the magnets will move apart slowly because it's very heavy things they're pushing, and so you'll be in the strong part of the magnetism for a larger t, right? The amount of t time will be large with large objects. So they'll spend a long time in the strongest repulsion force, and versus two very light things. So if I put two very light things on the magnet, they'll push apart very quickly, and so they won't be in the force very long. So just like gravity, it's a time-dependent force. It's about how long the force is being applied will decide how much energy you can secure from it. So clearly, heavy things are going to be able to get more momentum from the compression of the magnet than light things, because the magnets are going to fly apart quickly, and that's all you're going to get. I mean, they have a maximum speed, just like a spring. They can only go so fast just from the weight of the magnets. And anything you start adding a mass, the heavier the mass you add, the longer it will take the magnets to separate, meaning the longer the magnets will be pushing against each other. And you really have to see the magnets as doing that. Like every second, they produce a certain number of little pushing arrows. All right. And so if they're opposing each other for 1 second, then they get 9 of those arrows. And if it's 2 seconds, then it's 18 of those arrows. And if it's 3 seconds, then it's 27 of those arrows of force, of being in a circumstance that can be analogized as little rocks being thrown at it. So it's only 9 rocks if it's 1 second, and if you can spend 2 seconds being close together, then it's going to be 18 rocks, twice as much. So the heavier things moving slowly can acquire a lot more momentum because they're going to be taking advantage of the stronger force for a much longer period of time. So anyway, just another observation that I think makes it clear that you have to consider variables when you do experiments. And you have to understand how the mechanism actually works. And the fact is that springs and magnets and all these things are time dependent. And the more you can slow down the application of the force, take it over a longer period of time, the more force you can put into the object. Blah, 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 blah. I'd say especially in the case of magnets. Springs, I don't think it matters time-wise, because the only thing that matters is whether it expands, when it expands, when it finally expands, in the sense that the object leaves the spring. How much energy does the spring still have in it is the question. And the simple answer is, well, with a light object, there's a lot of energy left in the spring. And with a heavy object, there's very little energy left in the spring. That's the key takeaway. All right, so I'll call that enough of a video, I guess. I'll pause and see if something turns up.